Our solar system is packed with some seriously mind-blowing worlds. Just look around. You've got Io, a moon absolutely covered in a multitude of erupting volcanoes. There's Titan, rocking literal lakes and seas of liquid natural gas. Pluto features massive mountains and plains made of frozen nitrogen ice cream. Then you have Iapetus, the space walnut with its bizarre equatorial ridge, and Miranda, whose chaotic relief looks like it was drawn by a prehistoric artist in the Lascaux cave. And the list goes on and on. There are still plenty of wild worlds out there. So, against the backdrop of these cosmic freaks, it's really not surprising that a seemingly inactive, dull gray bulb like our moon might strike people as incredibly boring, especially since it's so familiar to us. Hundreds and thousands of generations of humans have looked at it, day after day. But, of course, the truth is far from boring. Next time you look up at the moon in the night sky, really think about it. Doesn't it look a bit strange to you? A bit special? Maybe even like something is wrong with it? Because the reality is, it is both strange and special. And in a certain sense, yes, something is definitely up with it. It raises a whole mountain of questions. In fact, some people use these anomalies as arguments to claim that the moon doesn't exist at all, or that it's completely artificial, or even that it's just a hologram projected onto a giant atmospheric dome. Today, we are going to tackle these exact questions. These are things that wouldn't quite stretch out into a whole standalone episode, but combining them all together into one big deep dive is exactly what we need. Is the Earth and the moon actually a double planet? Or maybe the moon is secretly the 9th planet of the solar system? Why is it so fundamentally different from other satellites, and why is it so ridiculously huge? And what's the deal with all its craters being the exact same depth? Could it really be artificial? Let's break it down. If we look at the absolute sizes of satellites in our solar system, calling the moon huge might seem a bit inappropriate at first. If we rank them, the moon only comes in 5th place. First, we have Ganymede, then Titan, then Callisto, and then Io. All of these are satellites belonging to the gas giants, planets that are many, many times larger than Earth. And our moon, in a direct matchup, loses to these largest moons in terms of pure size. But here's the catch. The moon has a completely unique, unprecedented ratio of its own size to the size of its parent planet. Let's look at the numbers. Even the largest satellite in the solar system, Jupiter's Ganymede, is 26.5 times smaller than its own planet. I've made a clear visual comparison right here to show you the proportions. Look at Jupiter with Ganymede, and now look at Earth with the moon. The radius of our moon is more than a quarter of the Earth's radius. We have a colossal satellite compared to our planet, the likes of which you won't find anywhere else. And just to be safe, let me clarify. I am talking about the 8 full major planets here. I'm not counting dwarf planets like Pluto yet. Well, precisely because of this unique relationship, some people, including top space agencies, call the Earth and the Moon a double planet, which we will discuss a little further. But this unusual relationship immediately raises a bunch of questions. Why did it turn out like this? What does it mean? Who designed it this way? It's completely obvious that the reasons behind the Moon's massive size are directly tied to how it was born. And apparently, it was formed in a rather unique way, one that differs drastically from the birth of most other satellites in our solar system. Look at the inner solar system, the rocky zone. Moons are incredibly rare here. Aside from our moon, there are only 2 others, Deimos and Phobos, orbiting Mars. But honestly, those 2 shapeless, lumpy globes are almost ashamed to compare themselves to our moon. Their diameters are a tiny 16 and 26 kilometers compared to the massive, almost 3,500-kilometer wide moon. The dozens and hundreds of other satellites that we can use for comparison all belong to the gas giants. And by the way, remember that we have to work only with the facts and objects we can see inside our own solar system. Why? Because we still don't know anything about exomoons, moons orbiting planets outside our system. We only have a couple of unconfirmed candidates so far. So, how do giant planets usually get their satellites? The primary method is called accretion. This process closely mirrors how planets themselves form around young stars. A small fraction of the dust and gas surrounding a newborn star forms a massive, swirling protoplanetary disk, inside of which planets eventually clump together. In the exact same way, the satellite systems of giant planets look like miniature star systems with their own protoplanetary disks. Due to the remnants of this near-planetary disk, satellites are born around the giant planet. This is proven by the fact that many of these moons lie in the exact same orbital plane as the planet's equator and have neat circular orbits. The second way is capture. Satellites can be independent objects that were formed somewhere else entirely but were later snatched by the giant planet's gravity. The orbits of these cosmic kidnap victims are usually messy. They are highly inclined relative to the planet's equator, and they aren't circular at all, but highly stretched out with high eccentricity. These can be small bodies like asteroids, or quite large ones, like Neptune's moon Triton, which is the 7th largest satellite in the solar system. But as far as we know, our moon didn't use either of these methods. Of course, there are other theoretical formation models, like a piece of the Earth breaking off due to super-fast rotation, but as many of you probably know, the main modern version of the moon's origin is the giant impact hypothesis. According to this model, the moon was formed from material thrown into Earth's orbit after a colossal collision with a protoplanet named Theia, which was roughly the size of Mars. This means the moon was not born in a calm, orderly way like most other satellites. Naively, you might look at it like this. If we draw an analogy between a star with planets and a planet with satellites, we usually see that planets are vastly smaller than their host stars. However, there are some wild exceptions out there in deep space, like the exoplanets TOI 5205b or GJ 3512b. These are giant planets with masses close to Jupiter, but they are orbiting tiny red dwarf stars. Such scenarios don't really fit into our modern theories of planet formation, and scientists are still studying these rare finds to understand how on Earth it happened. So, through normal evolutionary formation, getting such a massive satellite is highly unlikely. But through a violent collision of two bodies? On the contrary, two objects with the proportions and masses of the Earth and the Moon fit the collision model perfectly. But here, too, things aren't as simple as they look. Like I said, despite discovering thousands of exoplanets outside our system, we haven't found a single definitive exomoon yet. First, we need an important clarification regarding how the Moon formed after the crash. So, the collision happened and material was blasted into orbit, forming a disk. But what kind of disk? It turns out that in Earth's case, it was a partially evaporated disk. This means part of the rock literally vaporized into a scorching state of gas, while the other part remained as solid fragments of various sizes, basically stones and boulders. The authors of the study ran a massive series of computer simulations of protoplanetary collisions to see what kinds of disks and satellites you end up with. They focused specifically on rocky, Earth-like planets and icy planets, leaving mini-Neptunes and gas giants out of the equation for now. They simulated various crashes for planets of different masses, and here is what their models showed. Not all planet collisions result in a partially evaporated disk. Instead, on more massive planets, you get completely evaporated, purely gaseous disks. And in a 100% gaseous disk, large moons simply cannot survive. Because while tiny mini-moons, ranging from 100 meters to 100 kilometers in diameter, do start to clump together, the heavy gas drag in the disk slows them down. They lose orbital speed, spiral inward, and rain right back down onto the planet. Large satellites just don't have time to form. These completely vaporized, moon-destroying disks appear on more massive planets, specifically planets heavier than 6 Earth masses if they are rocky, and more than 1 Earth mass if they are icy. This happens because crashing into a more massive planet releases significantly more energy, causing the rock to evaporate completely. If the scientists' conclusions are correct, this helps us narrow down where to look for exomoons. We should look at Earth-like planets with masses less than 6 Earth masses if we want to find a large moon. But there's another huge takeaway. It is widely believed that for Earth, having a massive moon is a vital ingredient for life. The moon stabilizes the Earth's axial tilt, regulates our climate, and is considered crucial for the evolution of complex life. I previously noted that our moon is big because it took a different evolutionary path, a collision. But now we see that even a collision model doesn't guarantee a proportionally large moon. For rocky planets, this cosmic lottery is only possible within a very strict, narrow mass range. All right, fair enough. But what about the claim that the moon and the Earth are officially a double planet? Back in 2003, a publication came out with the bold title, "Welcome to the Double Planet." The article itself was covering the launch of Smart 1, the very first European spacecraft sent to the moon. But right there on the official space agency website, it explicitly stated that the Earth and the moon aren't just a planet and its satellite, they are a double planet. What are the arguments for this? Well, first off, there's the unique size and radius ratio we just spent all that time talking about. And honestly, that size ratio is pretty much the only argument. But when a statement like that is published not in some random blog, but on the official website of a major space agency, it causes a lot of people to think, well, then it must be an absolute scientific fact. These debates have been raging for a long time. First of all, whether a system is a planet and satellite or a double planet is fundamentally a question of terminology and human semantics. It just depends on what we agreed to call a pair of cosmic bodies. If we want a crystal clear answer, we need equally clear definitions of what a satellite, a planet, and a double planet actually are. As you know, these official definitions are written by the International Astronomical Union, IAU. They have a definition for a planet, though it still makes a lot of people angry. This is the infamous 2006 resolution that brutally stripped Pluto of its planetary status. Let me remind you that under this current definition, a body in our solar system must meet 3 strict criteria to be called a planet. It must be in orbit around the Sun. It must be massive enough to have pulled itself into a spherical shape. It must have cleared the neighborhood around its orbit. It was that third point that killed Pluto. But here's the funny part. What does clearing the neighborhood even mean? It turns out that out there near Pluto, in the deep, dark edges of the solar system, there are tons of similar objects in similar orbits, some even comparable to Pluto in size. It's as if Mars had a few clones running around nearby. But wait a minute, how far counts as outside the orbit? And how clean does an orbit have to be to count as cleared? If we are being strict, the Earth itself fails this test because its orbit is filled with near-Earth asteroids. And Jupiter shares its orbital path with a massive crew of thousands of Trojan asteroids. Sure, Jupiter is obviously way bigger than them, but they are right there in its neighborhood. The text of the IAU resolution doesn't give precise mathematical limits on this. That's why it's a definition that plenty of scientists still heavily criticize to this day. But hey, that's just the first term, and we'll deal with the loopholes later. Now, let's look at the term double planet. What clear, undeniable criteria must a two-body system meet to be classified as a double planet rather than a planet and a moon? Well, the International Astronomical Union simply doesn't have a definition for it. Seriously, it doesn't exist in their official regulations. So if you want to confidently look at official scientific documents to prove Earth and the Moon are a double planet, you're out of luck. Maybe these definitions will be written in the future, but right now they don't exist. However, there are less official, expert opinions based on specific physics. For example, people often bring up an argument based entirely on mass. Let's say two bodies share an orbit around the Sun and rotate around a common center of mass. Usually the larger one is the planet, and the smaller one is the satellite. But if their masses are exactly equal, a 1-to-1 ratio, then it's unequivocally a double planet. But a perfect 1-to-1 mass ratio is incredibly rare in nature. In reality, bodies will almost always have different masses, and most people will reflexively call the smaller one a satellite, even if it holds 1% of the total mass. Let's look at our system. The radius ratio between the Earth and the Moon is roughly 1-to-4, or precisely 0.27. But the mass ratio is a completely different story. It's about 1-to-81, or 0.012. In short, the Moon's mass is 81 times less than the mass of the Earth. So yeah, we are a very long way away from a balanced 1-to-1 ratio. But wait, size isn't the only way to define a double planet. There is another major factor scientists love to bring up: the barycenter, or the common center of mass. This is the exact point in space around which both cosmic bodies rotate. If you want to see perfect double systems where nobody has any doubts, look at double stars. You can have two red dwarfs or two sun-like stars dancing around each other. If their masses are roughly equal and their orbits are circular, they rotate around a barycenter that sits right in the empty space between them. It's just an imaginary point in physics, but both stars loop around it. But when one body is significantly heavier than the other, the story changes completely. Take the Sun-Earth system. Because the Sun is an absolute unit, the barycenter of their orbit lies deep inside the Sun, practically at its very center. Because of this, some astronomers suggest a clever rule. If the barycenter of a two-body system lies in empty space, outside of both objects, it's a double planet. If the barycenter is trapped inside the main body, it's just a planet and a satellite. Under this rule, we actually have a perfect double planet in our solar system. Say hello to Pluto and Charon. Even though Pluto is heavier, Charon is massive enough to pull the system's center of mass completely outside of Pluto's surface. Their mass ratio is about 1-to-10. So, what about Earth and the Moon? Well, our barycenter is not at the center of the Earth. It's actually offset quite a bit, sitting about 4,650 kilometers away from the core toward the surface. But since the Earth's radius is about 6,371 kilometers, that barycenter is still buried deep underground, roughly 1,700 kilometers below our feet. So, by this logical physical criterion, the Earth and Moon don't qualify as a double planet. Pluto and Charon fit the bill perfectly, but our system doesn't. But here's the ultimate cosmic irony. According to the official IAU rules, Pluto isn't even a planet anymore. So how can Pluto and Charon be a double planet if the main body is just a dwarf? As you can see, there is still no official definition or consensus. By unofficial rules, Earth and the Moon don't quite make the cut. But while I was digging through various scientific sources, I stumbled upon a mind-blowing plot twist. I found a paper published in an actual academic journal that suggested something even crazier. It didn't say the Moon was a co-planet. It claimed the Moon is actually the 9th planet of the solar system. And you're probably like, wait, what? Let's look at the receipts. Back in 2017, a paper was published in the International Journal of Astronomy and Astrophysics titled, "The Moon Meets All Requirements of the International Astronomical Union to be Called a Planet." The author spent a lot of time pointing out the sloppy definitions of satellites and double planets that we just talked about. But then, they boldly claimed that our moon easily ticks all three of the IAU's planetary boxes. Let's test this claim. The moon is massive enough to have pulled itself into a neat sphere. It easily beats Pluto in size, so no arguments here. Has it cleared its orbit? This is where it gets tricky. Obviously, the Earth did 99% of the heavy lifting, but the paper argues that the moon is massive enough that it technically helped clear the Earth-Moon orbital zone. A bit of a stretch, but let's hear them out. Does it orbit the sun? Your instinct probably screams, no, the moon orbits the Earth, and the Earth orbits the sun. But physics has a massive trick up its sleeve here. How does the moon actually move around the sun? If you picture it looping around the Earth in giant curly spirals as we fly through space, you're dead wrong. If we look at the scale correctly, the moon is moving forward along the Earth's orbital path, gently weaving back and forth. It moves from the inside of Earth's orbit to the outside. No loops, no crazy spirals. If you zoom out, the blue line of Earth's orbit and the yellow line of the moon's orbit completely merge. They travel together, with Earth just doing a tiny, wobbly dance. But you might object, wait, if we judge a planet solely by its trajectory around the sun, wouldn't that make giant moons like Europa or Titan planets too? The paper has an answer for that, and it comes down to a gravitational tug-of-war. For Jupiter's or Saturn's moons, the planet always wins the gravity war. Those moons are firmly under their parent planet's control. But our moon is physically more controlled by the sun's gravity than the Earth's. According to the author, this unique gravity dynamic means the moon is technically orbiting the sun first, and its orbit is relatively cleared. Therefore, boom, the moon is the ninth planet. It's a fascinating theory, but don't go rewriting the textbooks just yet. No serious astronomer has accepted this. And it probably doesn't help that the journal where this paper was published belongs to a publisher with a notorious reputation, often flagged as a predatory or garbage publisher. These outlets will print almost anything for a fee, which explains why the author didn't publish this in a top-tier peer-reviewed journal. While the ninth planet claim is a massive stretch, this paper does prove one thing: our astronomical definitions are still incredibly messy. Speaking of messy, let's transition into a story that belongs in a Stop What segment. Conspiracy theorists absolutely love claiming that the moon is an artificial, hollow alien spaceship. And one of their favorite proofs is the mystery of the lunar craters. You've probably seen these claims online. Why are all craters on the moon the same depth? Whether they are tiny or hundreds of kilometers wide, they all seem to stop at the same flat level. Their logic is simple. A giant asteroid should blast a proportionally deep, gaping canyon into the moon. But we don't see that. So what's their brilliant conclusion? They claim the moon has a thin layer of dusty dirt on top, but underneath sits a super strong, indestructible, hollow metal sphere that shields the inside of the alien base. It sounds like a fun sci-fi movie, but the entire theory falls apart because of two simple things: basic facts and gravity. First of all, lunar craters are not all the same depth. That's a flat-out lie. Small craters can be just a few dozen meters deep. Meanwhile, the famous Tycho crater is almost 5 kilometers deep, and others go even deeper. So the premise of the conspiracy is just factually wrong. However, there is a grain of truth that confuses people. As craters get wider, their width-to-depth ratio changes drastically. For a massive crater like Copernicus, which is 93 kilometers wide, the depth is only about 3.8 kilometers. Major craters are incredibly flat, looking more like shallow plates than deep bowls, whereas tiny craters look like deep, steep cups. So, why aren't giant craters proportionally deep? To blast a crater that is hundreds of kilometers wide, you need a massive asteroid moving at hypersonic speeds. When that kind of kinetic energy is released, solid rock doesn't just crack, It behaves exactly like a liquid. Remember the IAU planet rule about being massive enough to form a sphere? When a celestial body reaches a certain mass, its own gravity forces it to maintain hydrostatic equilibrium. Gravity simply will not allow a massive, unstable, 50-kilometer deep canyon to exist on a body the size of the moon. The weight of the surrounding rock would cause the canyon walls to instantly collapse, pushing the crater floor upward. Gravity forces everything to smooth out. If the moon didn't have gravity to clean up these impacts, it would be a crooked, unstable, jagged mess of space rubble. What I love about conspiracy theorists is that even their wildest mistakes give us an amazing opportunity to talk about how the universe actually works. Not everyone asking about crater depths is a conspiracy nut. Some people are just genuinely curious, and clearing up that confusion is exactly why I love making these videos. No matter how many times we look at it, the moon will never be just a boring gray rock to me. There is still so much to explore, and if you want to keep digging into these cosmic mysteries, let me know in the comments. Hit that subscribe button, and I'll see you in the next video.